Welcome to this video. And in this video, I discuss the concept of state space representation for discrete time systems. State space representation for discrete time systems. Now, given the pulse transfer function of a discrete time system defined by y of z over u of z, which is a polynomial in z over a polynomial in z defined by b naught z power n plus b1 z power n minus 1 plus all the way up to bn divided by a polynomial in z defined by z power n plus a0 z power n minus 1 plus all the way up to an, where b0 to bn and a0 to an are the coefficients of the polynomial in z in the numerator and the denominator respectively. Then we can obtain the state space representation of the system by determining the n first order difference equations, which may be combined into first order vector matrix difference equation defined by x of k plus 1 is equals to a matrix G multiplied by x of k plus a matrix H multiplied by u of k, where that is our state equation. And the output equation y of k is equals to a matrix C multiplied by x of k plus a matrix D multiplied by u of k, where of course G is the state matrix, H is the input matrix, C is the output matrix, and D is a transition matrix. Then the system's state space representation can be written in different canonical forms, just like in the state space representation of time continuous systems discussed earlier. We can represent the system's state space in the following canonical forms. The first one is the controllable canonical form. The controllable canonical form of the state space representation, where the state equation of the system can be written as, so the set of the first order difference equation representing the state equation as x1 of k plus 1, x2 of k plus 1, all the way to x n minus 1 k plus 1 into xn of k plus 1. So this is the vector in x of k plus 1 will be equal to the matrix G, where matrix G will be defined by the first row will start with 0, 1, and then all the other terms are 0. Then starts with 0, we shift the 1 to 0, 1, with all the other terms 0, up to the second last row, which will be a row of all zeros apart from the last term, which is a 1. And then the last row will be a row based on the coefficients of the denominator of the pulse transfer function as negative an minus 1, negative an minus 2, all the way up to negative a1. Multiplied by x1 of k, x2 of k, all the way up to xn minus 1 of k and xn of k plus the matrix H, which will be a matrix of all zeros apart from the last term as 0, 0, 0, 1 multiplied by u of k. That is the state equation. The output equation is obtained as y of k is equals to the matrix C, where C will be given by Bn minus An B0, Bn minus 1 minus An minus 1 multiplied by B0, all the way up to B1 minus A1 B0 multiplied by x1 of k, x2 of k, all the way to xn of k plus B0 u of k. That means the matrix D will be a constant, B naught, and the matrix C is obtained from Bn minus An B0 all the way up to B1 minus A1 B0. And this is the controllable canonical form of the state space representation for discrete time systems. The second method is the observable canonical form. The observable canonical form. Again, given the same pulse transfer function, we can write the observable canonical form of the state space representation as follows. The matrix G is obtained by transposing the matrix G in the controllable canonical form. The matrix H is obtained by transposing the matrix C in the controllable canonical form. The matrix C is obtained by transposing the matrix H from the controllable canonical form, while the matrix D remains a constant P naught. Therefore, we can write the observable canonical form of the state space representation as x1 of k plus 1, x2 of k plus 1, all the way to xn minus 1 of k plus 1 into xn of k plus 1. That is the vector in x of k plus 1 will be equal to. So we transpose the matrix G in the controllable canonical form to obtain 0, 1 with all the other terms as 0, 0. The second row will be 0, 0 with all the other terms as 0, 0. Up to the second last row, which will be a row of 0, 0, 0, and only the last term, which is a 1. And the last column will involve negative an minus 1, all the way up to negative a2 and negative a1. All this multiplied by x1 of k, x2 of k, all the way to xn minus 1 of k, xn of k, plus the matrix H, we transpose matrix C from the controllable canonical form to obtain Bn minus An B0, Bn minus 1 minus An minus 1 B0, all the way up to B2 minus A2 B0 and B1 minus A1 B0 multiplied by u of k. The output equation is written as y of k is equals to, for the matrix C, we transpose the matrix H from the controllable canonical form to obtain a matrix of all zeros apart from the last term as 0, 0, 0, 1 multiplied by x1 of k, x2 of k, xn minus 1 of k, and xn of k, plus the matrix B, which remains unchanged as B naught U of k. And that is observable canonical form of the state space representation. Lastly is the diagonal canonical form. The diagonal canonical form of the state space representation. The diagonal canonical form is obtained so long as the poles of the pulse transfer function are all distinct. That means the denominator of the pulse transfer function can be factorized, and all the factors, they are no repeated roots or poles for the denominator polynomial of the pulse transfer function. If it's possible to write our transfer function or our pulse transfer function in terms of its partial parts, that means our y of z over u of z, which is written as a polynomial in z defined by that numerator polynomial in z over z power n plus a1 z power n minus 1 all the way to an. If this can be written in partial parts as b0 plus a constant c1 over z plus p1 plus c2 over z plus p2 plus all the way up to a constant cn over z plus pn, where p1, p2, all the way to pn are the terms or the factors or the poles of the given transfer, that is denominator polynomial of the pulse transfer function. Then, given the values of the residues of the poles and the poles of the given transfer function, we can obtain the diagonal canonical form of the state space representation as follows. The state equation is written as x1 of k plus 1, x2 of k plus 1, all the way to xn minus 1 of k plus 1 into xn of k plus 1. Our vector in x of k plus 1 will be equal to, the matrix G is a matrix of all terms being 0 apart from the terms on the major diagonal, which are obtained as negative p1, 0. All the other terms are 0. Then 0, negative p2 with all the other terms as 0. Up to the second last row, which will be a row of all terms apart from the second last term as pn minus 1, 0, and then the last row as 0, 0, 0, negative pn, multiplied by x1 of k, x2 of k, all the way to xn minus 1 of k, and xn of k, plus the matrix H is a matrix of all terms being 1 as 1, 1, 1, 1, multiplied by u of k. That's our state equation, where the matrix G is a matrix of all terms being 0 apart from the terms on the major diagonal, which are the negated terms of the poles of the given pulse transfer function. The matrix H is a matrix of all terms being 1s. The output equation is written as y of k is the matrix C, where C constitutes of the residues of the poles as C1, C2, all the way to Cn minus 1, Cn, multiplied by x1 of k, x2 of k, all the way to xn minus 1 of k, xn of k, and the matrix D is a constant B naught U of k. And that is the diagonal canonical form of the state space representation of discrete time systems. Let's take an example and try to obtain the state space representation in the three different forms. So for example, given the system defined by the pulse transfer function, or given a discrete time system defined by the pulse transfer function y of z over u of z is equals to z plus 1 over z squared plus 1.3z plus 0.4. We are to obtain the state space representation of the system in the controllable, observable, and the diagonal canonical forms. So we start with the controllable canonical form. It's good to note that this being a second order system, the denominator can be written as B0 plus B1Z plus 1 or B2 over Z squared plus A1Z plus A2, where our B0 is 0, B1 is 1, and B2 is also 1. Our A1 is 1.3, and our A2 is 0.4. The state equation can be written as x1 of k plus 1, x2 of k plus 1, as the vector in x of k plus 1 will be. The matrix G will be 0, 1 for the first row, and then negative A2 and negative A1, negative A2 and negative A1 into x1 of k and x2 of k, plus the matrix H is all terms 0 apart from the last one, which is 0, 1 multiplied by U of k, which we can write as x1 of k plus 1 and x2 of k plus 1 to be the matrix. So you'll have 0, 1, negative A2 is negative 0.4 and negative 1.3 into x1 of k and x2 of k, plus the matrix H, which is 0, 1 multiplied by U of k, and that is the state equation. The output equation y of k is defined by, so it will be B2 minus A2 B0, B1 minus A1 B0 into x1 of k, x2 of k, plus B0 U of k. Of course, B naught is 0. So our y of k can now be written as the matrix C, which is B2 minus A2 B0. But because B0 is 0, the whole of these terms will be 0. That means we'll have B2 and B1. So B2 is 1 and B1 is 1 into x1 of k and x2 of k. And that is the state equation and the output equation in controllable canonical form. The second method is the representation in observable canonical form. Observable canonical form. So our system's state space representation can be written as x1 of k plus 1, x2 of k plus 1 will be equal to So we transpose matrix G to obtain 0, 1, and then negative 0.4, negative 1.3 into x1 of k, x2 of k, plus, then we transpose matrix C to obtain our matrix H as 1, 1, u of k. And finally, our y of k as our output equation will be, we transpose matrix H to obtain 0, 1 into x1 of k, x2 of k. And that is the observable canonical form of the state space representation. Lastly, number 3 is the diagonal canonical form. For us to be able to write the diagonal canonical form of the state space representation, we've got to write the pulse transfer function in partial fraction form. Our y of z over u of z can be written as z plus 1 over the factors of the denominator, which are z plus 0.5 into z plus 0.8, which we can write as A or C1 as the constant C1 over Z plus 0.5 plus C2 over Z plus 0.8. From this, we calculate the values of C1 and C2, and we obtain the values of C1 as C1 will be 5 over 3, and C2 will be negative 2 over 3. Therefore, we can write our pulse transfer function as 5 over 3 over Z plus 0.5 minus 2 over 3 over Z plus 0.8. The state equation will be obtained as x1 of k plus 1, x2 of k plus 1 will be equal to, the matrix G is a matrix of all zeros, apart from the terms on the major diagonal, which are the negated terms of the poles as negative 0.5, negative 0.8, and then 0, 0 into x1 of k, x2 of k, plus the matrix H is a matrix of all ones, it's 1, 1, multiplied by u of k. Our output y of k will be obtained as, so we use the terms for the matrix C as the residuals of the poles as C1 and C2, obtained as 5 over 3 and negative 2 over 3 into x1 of k, x2 of k. Of course, our B0 is 0, and this becomes the state space representation of the system in diagonal canonical form. And that is the end of my presentation, where we've been able to look at the state space representation of discrete time systems in controllable, observable, and the diagonal canonical forms. Otherwise, thank you for watching that video.